Welcome to session 1 of the Maximum Likelihood Lecture. So here we're going to explore a particular estimation method. And to do so, we need to understand how we might fit a distribution to data. So let's suppose that we have a random variable, y in this case, and let me change colors here. It wasn't so quite so dramatic. Y, and it has a normal distribution with some mean mu and sigma squared. But we don't know what mu and sigma squared is. So it really is, we're specifying y as coming from a family of distributions, normal with a mean, mu, and sigma. And we don't really know the particulars of the parameter. That's what we want to estimate, is the mean or the variance. So how might we do this? Well, let's suppose that right here is our histogram, and this is this part of the graph. This is the histogram of the actual data. It doesn't really matter that, I kind of have it drawn here as a triangle. That's accidental. It's just some histogram. And we want to come up with what might be a good specification for a normal distribution that could produce such data. So let's suppose that we start out speculating that right here, and I'll just say that's 0, is the mean, and we have some standard deviation that represents the stretch of the distribution this way, the variance. And we can ask the question, if this were the distribution, what is the probability that we would get the data that we got? So if this is what we were drawing our random variables from, would we get this number represented by this part of the histogram, number of observations from that distribution? Well, what's the probability of doing so? So we would calculate under this curve, which goes all the way down like this. I kind of missed it up at the top here, but basically we're stretching this curve out. The probability of getting data here, well, clearly it's going to be very, very small, since these particular values for a random variable have very low probability under the distribution being considered. So the probability of getting realizations from the random variables that underlie the data that give a histogram as shown is very small. Well, so what might we do? Well, we might switch, and we might say, well, let me erase a little bit here. Let's move this distribution this way a bit. And maybe we consider this distribution, which doesn't look normal, but let's pretend it is normal for the moment, not very symmetric. And we could calculate the probability with this mean and this standard deviation of producing this histogram of data. And it's going to be a lot larger. You notice that the values of x are now much more common relative to the density specified here by this curve. But we probably could do better. All right? We could probably move it even further and move it over so that it goes, maybe lines right up with respect to the mode of the data. And this is going to give us a higher probability under this particular potential model for a normal of this data. Well, maybe so, but we could even do better perhaps, because notice how spread this distribution is. Well, perhaps instead what we have, I guess I'll go back to my red pen, is let me just take a different distribution. Let me leave it there, but I am going to shrink it in a bit. Now with the same mean that I had before, but now a variance that only spreads it out this far, perhaps this is better. And indeed, this is by looking at the histogram. This is going to capture that histogram much more faithfully than did this original blue one over here. So basically what we've done is we have moved the distribution around and stretched it back and forth until it was a distribution that would make the data that we actually got, which is the histogram here, very highly probable. Well, that's the basic idea behind maximum likelihood estimation, is that we are going to posit essentially a family of distributions. By that I mean we have a a functional form for a distribution, but the parameters, or at least one of the parameters, are not known. And we're going to move those parameters around until the specified model with the parameter value that we move to makes the data most likely or highly probable. And that's going to be the basic idea behind maximum likelihood estimation. All right, move down a little bit here, stretch and shift. This is just simply stating what I've said before. And so we say that a model I, let's say, is more likely than model J, two different specifications, if the model I makes the data more probable than model J. So we could state it this way: probability of the data under a specification model I being greater than the probability under specification of model J. And that would mean that this one we would consider as being more likely. Question becomes, what does the probability model? Here you notice that the likelihood function is really being fit to the data. The data are kind of dictating what would be considered the better model. It's still the case for most uses of maximum likelihood that the specification is presumed to be capturing the probability of the data generating process. If, however, we made that presumption without actually making any further restrictions on the possible models to be considered, and we searched across all possible models, which we will end up with always, is that, well, it's the empirical likelihood. And the empirical likelihood is just to say that it is the histogram itself. The most likely distribution is just that distribution that matches the histogram. And this is called the empirical likelihood. That's not really very useful for much of what we use maximum likelihood estimation for. Not completely without utility. We can use empirical likelihoods for many useful reasons, but for most of what we do in maximum likelihood estimation, we do not use the empirical likelihood, but we rather have a parametric distribution specified, and then we estimate the parameters for that distribution. And we may then compare that to the maximum likelihood estimate for a different family of distributions. I may first estimate a normal distribution, and then I may compare that to an estimate based on a gamma distribution to try to rule out which one is not likely to produce the data, and therefore provide greater favor to the one that is a closer match. So the likelihood function itself is thought of as a function of the parameters then, because that's what we're varying, and the data are considered fixed. So where we have a probability measure associated with the data and it's parameterized, as a likelihood function, the function that we're going to be searching over and changing, it's the parameters itself that are considered variables, not random variables, but variables. It's the parameters that we are going to search over to try to maximize this function. So the likelihood function is considered a function of the parameters, whereas a probability is considered a function of the data, and if it's a family probability, it's a function of the data and the parameters. So the likelihood of a model is the probability of the data given the model. So here I just kind of represent that the probability goes from y as values from random variables to the unit interval, and the likelihood goes from parameters to that unit interval. So it is a measure of support regardless of the actual data generating mechanism. It's a way of doing a comparison of models, not necessarily to the truth, because we don't know what the truth is. We assert the model. We say, suppose it is a normal, suppose it is a gamma, and what is the maximum likelihood estimator based on that presumption. Now you can use various tests to compare models, but we don't actually know what the underlying data generating process model is. So from that perspective, it really is a measure of how well the the data are being captured by a particular posited model. Also notice that in its own right, maximum likelihood estimation does not typically include uncertainty of the model itself. It includes uncertainty with regard to the estimation of the parameters, but not the fact that I decided to pick a gamma distribution rather than, say, a normal distribution. There are ways to account for model uncertainty. We will not cover that in this course. So, the definition then of a likelihood function is the probability of the data, and it's specified as a function of the parameters of that distribution. So as I said before, here's kind of how you can think about the two different functions. So let's suppose, for example, that we have a data set that is comprised of 3 vectors of data. In other words, we have a bunch of measurements on, let's say, 3 individuals. So the first vector has a set of measurements, the second a set, the third set. And let's suppose that the underlying random variables are all independent. But let's suppose that the elements of the random vectors yi are not necessarily independent within. So what do I mean by that? I mean these are independent, but these may not be. Pointing here as if these were random vectors as opposed to the actual data up here. So as random vectors, these might be independent as we specify, but the random variables within a random vector are possibly dependent. Well, the likelihood would be the probability associated with the joint distribution of the data that come from the random vectors y1, y2, y3, and it's specified as a function of parameters. Notice that I'm using a semicolon here. I'm not using the classic probability of x or y this way, because this is a conditional statement of random variables, and the parameter itself is not a random variable. It is considered a fixed quantity. It is a parameter that we specify. And this is actually somewhat of a difference between the frequentist approach to maximum likelihood estimation and the Bayesian approach to using the likelihood function. And we don't need to concern ourselves actually with the details of that. If you're interested, you can easily find that in the statistics literature. But for this course, we will stay with the frequentist approach. So, since we said that y1, y2, and y3 are independent, then this joint distribution will break down. Well, at first we can break it down this way regardless of being independent. And that is to say that y1, this joint distribution of y1, y2, y3 is the probability of y1 given y2 and 3 times the probability of y2 given y3 times the probability of y3. And since they're independent, they are really just the product of the marginal distributions. Probability of y1 times the probability of y2 times the probability of y3. Notice that these are indexed by 1, 2, and 3 to indicate that they don't actually have to be the same in our specification. If they were to be considered the same, then they would be considered identically distributed. So above we've specified here that they are independent, and we may also specify that they have the same distribution, which would be identically distributed if we wish to do so. But before we impose that, the general likelihood could be written then as the product, right? That's we're doing multiplication up here, so the product of these probabilities. Now, how do I come up with these distributions? Well, if theory says the distribution could be a particular one, well, then we would use, in this case as my example, let's say negative binomial, then we would use a negative binomial. And our maximum likelihood estimation of the negative binomial could actually be used to test the theory itself. This is not very common. It's not very common, at least in health services research and policy, that your theories are going to tell you the distribution of the random variables. But if it were the case, then you would specify it as the theoretically implied distribution, and you would use this to test whether it is plausible to believe the theory. Another way is that if you simply know it by the design of the experiment. And if that's the case, well, then you would use the distribution that the underlying random variables actually have. Right? So if you're going to flip a coin and multiple times up to the point at which you first get ahead, then that's going to have a very specific distribution. And you would know that ahead of time. Otherwise, if theory did not give you the distribution, or you did not know it by the design, typically what we have is we have to come up with a plausible model for the underlying distribution. This is done by specification tests. And so we will use specification tests to see whether a particular candidate distribution is a plausible one. And in addition to the specification of individual functions, we can also cross-compare different distributions to identify the statistically adequate distribution. Now, the above example, if it was completely IID, you would come down to going I from 1 to n now, because each of the random variables are identically distributed, and it would just be the product. So this is really the key point, is going to be a likelihood function is going to come down to the product of the probabilities of the independent random vectors in the data generating process. So now the next thing is to go from the likelihood to what's called the log likelihood. Simply put, it is the log of that probability. So this is the likelihood here. If we express it, think of it as a function of theta. You take the log of it, and that's the log likelihood. Well, the advantage of this part is if you take the log of the likelihood, which the likelihood itself is the product of probabilities across the independent components of the probability itself in the data, it becomes the sum of the log of the probabilities. And so we went from having to work with products to working with sums. This will be a great advantage. So, for example, if we had y1 to yn identically independent and identically distributed random variables, then we would come up with the sum of the log of the probability associated with each one. Put a little j in there. Now notice that the log of a function is a monotonic transformation, and so the value that maximizes the likelihood will be the same value that maximizes the log likelihood. So when you're trying to find the maximum likelihood, you can just as well look at the maximum log likelihood. There will be a number of mathematical benefits to using the log likelihood when it comes to evaluating the properties of the estimator based on maximizing the log likelihood. But there's a couple of pragmatic benefits as well. One is the derivatives are easier to deal with, and we won't need the derivatives. Why is that? Well, if you're going to take the derivative of the product of a certain function with respect to whatever values you're doing, this derivative is going to be much more difficult to deal with. Just go back to your basic calculus and notice that when you're taking derivative products, it gets to be much more of an onerous process than it is to take the derivative of the sum. All right, the derivative of the sum is going to be the sum of the derivative. It's a linear operator. So the derivatives are easier. Also, it has to do with computation as well and the precision of the numbers. Probabilities can be very small. The product of, let's say, you've got 10,000 data points. The product of probability associated with 10,000 is very small. Notice that the probabilities themselves are all going to be between 0 and 1, so you start multiplying things between 0 and 1 and do that over a large number of data points, this becomes an extremely small number. On the other hand, the log likelihood is summing the log of those probabilities, and that in fact is usually very easy to deal with, somewhere in the order of negative 15, negative 50 or whatever as it starts getting very small, but you're still in a very easy range of numbers for computational purposes. So the log likelihood has some practical utility to them beyond the mathematical utility that will come in and looking at the specification of the or the properties of the estimator itself. Let's also look at something called the conditional likelihood. So let's say we have data based on random variables y and x. Our parameters are actually a vector of two parameters, alpha and beta. And we're going to look at the probability then of the data given theta, which means the probability of y given x times the probability of x. Okay? So it may fall out that you have probability of y given x with the parameters of alpha and beta, and the probability of x with the parameters of beta. We are going to end up at, if we are not interested in beta under certain circumstances, we will just need to look at the conditional distribution itself. So let's say, for example, that alpha and beta themselves don't intersect, which means that the parameters in alpha are not the same as the parameters in beta. Okay, there's no essentially constraints across alpha and beta either, so that beta does not directly inform alpha or vice versa. In other words, our probability of the data is the probability of y given x, here's alpha, and the probability of x, and there's beta. Well, if that's the case, and we're only interested in alpha, then all we need to look at is the probability of y given x alone, the conditional likelihood. You can see this because if you take the probability and log it, you will get the log probability of y given x with the alpha parameter plus the log of x with the beta parameter. And if you are going to maximize only with respect to alpha, this is all that you're interested in, then this is the only component that is going to be of use. So this is one of the key strategies in looking at conditional distributions is maximum likelihood estimation of the conditional likelihood function. We will deal a little bit later with questions of using these other parameters, which are typically going to show up over here, a different kind of parameterization, but where we deal with parameters we're not really interested in something called profile likelihood, but for the moment we will put that aside. So here's an example. Let's say our conditional distribution random variables y given x has a Poisson distribution for all x. And the parameter lambda is therefore specified as e to the beta x, let's say. Now, what's important just to note on the side is that if you have a conditional distribution, and that distribution has a particular form, for example, in this case, it's a Poisson, and a Poisson has a single parameter lambda, then what makes it conditional in a way that's non-trivial must be that the parameters in the model must be a function of the x's. That has to be the case. And this is how you can think of writing up specifications for conditional models. You can take the specification of what y is intended to be, in this case Poisson, and then simply specify the parameters in the model as a function of the variables you're going to condition on. Because that's the only way that the conditional distribution can, in fact, be non-trivially conditional. It can't come in any other fashion. It must go through at least one of the parameters. So in this case, I'm going to say that lambda is equal to e to the beta x. So our density function for this is specified here as e to the negative lambda times lambda to the yi divided by y factorial. And if I'm going to allow this to be a conditional distribution on x so that my lambda is specified as above, then you just plug it in for lambda. And there you have the conditional density, okay, which I can rewrite this way. Now, technically speaking, the likelihood is a probability. Probabilities are positive, and therefore we can take the log of the likelihood. Now, this part of it is going to be true even with the following caveat. You'll notice that I did not write a probability up here. I'm writing densities. And much of maximum likelihood is actually done with respect to densities rather than functions that relate directly to the probabilities. This can cause problems, and I will explain it later in another section of this lecture, another session of this lecture. But at the moment, I'm going to just talk about likelihood functions in terms of probabilities, but I may actually write them actually in terms of densities, because that's how we quite often are going to implement maximum likelihood estimation. In fact, some people will consider the functions written in densities as defining the likelihood or the log likelihood functions. As I said, that's technically not actually going to be correct in some instances, but nonetheless, barring those particular instances, it is probably one of the most common ways of operating with likelihood functions. And again, I will get back to that in a few sessions from now. So looking at our log likelihood expressed in terms of the densities, it's going to have to do with our log of this density. You take the log of the density above, up here, and you get this. Now I want to maximize this log likelihood with respect to beta. And you'll notice that beta shows up here and beta shows up here, and it does not show up in this term. This is a constant. Well, what maximizes this whole function will be the same thing then that maximizes this part of the function here. I don't need the constant. So I really could only program, if I wanted to, this part and maximize this component of the function. So there's two parts. One is we only need the conditional likelihood sometimes. And moreover, we don't even need the full likelihood. We can drop those things that are constant. So in a general sense, let's say that I have y given x has some distribution where the parameters are specified as a function of x and some other set of some vector parameters beta. This would be what I want to set up in my model to be able to get my maximum likelihood estimation. I will base it on this specification. So, for example, let's suppose that this gives us the relationship between the variables y, z, and x, as well as variables eta and epsilon. Eta and epsilon are going to be considered unobserved. So the observed variables are y, z, and x. The parameters are alpha and beta in this particular function. And you can think of epsilon, we're going to assume, has a beta distribution, which means it'll go from 0 to 1, which means it really is going to scale from the top curve down, 0 to 1. All right, if epsilon is equal to 1, you get just this component of it. Let's do a little switching around here. You do just this component of it, and that is this curve. It's representing here for a fixed eta. Since eta is not observed, it's going to cause that curve to be fuzzy. But the epsilon part is scaling it this way. So let's assume that epsilon is beta. Let's assume that eta is a normal distributed variable with a mean of 0 and a variance of sigma squared. Beta has gamma 1, gamma 2 as its parameters. So if we take the log of the above function, we have the log of y is alpha transpose z, beta times the log of x, and then this log epsilon plus eta. And these are unobservable. This is a particular error term you could think of. Well, One possibility would be to go ahead and use a least squares estimator, ordinary least squares, although actually, it depends on the nature of it as to whether you get fancier than that, but basically some least squares estimator. And if the data, if we have a large enough sample size, this can be fine. If instead we want to pursue this by maximum likelihood, which if we can get the proper specification would make it an efficient estimator, we might still use OLS or a regression function to begin with in order to get the initial values to plug into our algorithm for maximizing the likelihood function or the log likelihood function. But let's consider now for the moment how we would go around specifying a likelihood function. Well, we consider u then, we can solve for u, right? This part is u, so u is going to equal to log y minus this part, right? So here we go, u is equal to log y minus quantity alpha z plus beta log x. We need to know what the distribution of u is, and it's parameterized by alpha and beta, because this is what we want to ultimately do. We want the log likelihood associated with the probability of getting u with the parameterization theta. Well, what is the distribution for u? Well, it's going to be the distribution of a log beta plus a normal, right? Because what is u? U is the log of epsilon plus eta. Epsilon is a beta, so the log of a beta plus a normal, right? Here's my beta, here's my normal. And I now then want to estimate the parameters associated with this overall model. So how do I do this? Well, we're going to use a variable transformation approach. Okay, so u is log epsilon plus eta, and I'm going to assume that eta is independent of epsilon. And this is an assumption. It's an independence assumption. And as we do with so much in statistics, there are going to become a point where we have to make assumptions. And in this case, I'm going to proceed with this assumption in mind. So first, I want a distribution of log epsilon, right? I know that epsilon has a beta distribution, but I don't know what log epsilon is. So we will do this by saying a new variable psi is equal to log epsilon, therefore epsilon is equal to e to psi, and the derivative d epsilon d psi is equal to e to the psi. Now, we know that epsilon has this density associated with it because this is the beta distribution. And so now if I plug in what I need, I can identify that psi therefore has the distribution which is specified as what I have here in the beta distribution, but it also has the derivative with a variable transformation attached to it. And if I just write the beta function, not distribution, but beta function of gamma 1, gamma 2 is just b, just for a shortcut, we end up with psi having the PDF of this function. So we have psi is the beta function still at gamma 1, gamma 2 times e to the gamma 1 psi times 1 minus e to the psi quantity to the gamma 2 minus 1. Okay. So that is our density associated with psi. So therefore we can ask, what is the distribution of u? Right? I know psi now has a certain density, which I just did above, and I know this has a normal density. So how do I get the distribution for u when it is made up of two random variables? Well, we need two equations, essentially. Or more specifically, when it comes to the techniques here that we're using, we actually need the joint distribution associated with two random variables. It's the same concept of essentially needing two equations in order to solve for two unknowns. Well, this one, u equal to psi eta, comes from the specification of the problem. I need a second one. Well, here I can just do it instrumentally. In this case, it will turn out that just setting a new variable v equal to eta will be sufficient. Sometimes you will set a new variable v equal to something else, and you can just, with a little bit of work, you can figure out what's the best specification to make the derivation of the distribution easiest. But in this case, I'm just going to literally just set v equal to eta. So that means that psi is equal to u plus v, and eta is equal to v. And I go and I get my matrix of derivatives. Derivative of psi with respect to u, derivative of psi with respect to v, derivative of eta with respect to u, derivative of eta with respect to v. I take the determinant of that. So I've got 1, 1, negative 1, 0, and 1. Take its determinant, and that gives me 1. All right, so the joint distribution is going to be specified as, since remember that they're independent, is going to be specified as the two distributions times the derivative, which is 1, so that doesn't really change much. And here I notice that I've just shortcutted, put k, so I don't have to write it up there, as 1 over 2 sigma squared. And so my joint distribution in terms of u and v is going to be plugging in the quantities for u and v, all right, and the derivative, and I get the density for the one times the density for the other, again times the derivative. And that's going to give me the joint distribution between u and v. Well, this sets me up nicely because I want the distribution of f of u. Well, now, if I've got f of uv, I need to simply integrate out v. All right? If I integrate out v, take this joint density, integrate out v, I get f of u. And this is the one that I want to do my likelihood based on. So in this case, what I can do is I can, for each data point, I have their yi, I have their xi, I have their zi. I can put in candidate values for alpha and beta, and therefore for those candidate values for alpha and beta, I can calculate a u. I can calculate the density of u, therefore, by taking this above distribution up here, this distribution, and integrating out v. Most likely I won't be able to do it in a closed form, but that's okay. From our last lecture, I will be able to do this integral using maximum simulated likelihood, or I use maximum simulated likelihood to estimate the parameters, because I will use Monte Carlo simulation to estimate this integral for everybody in the data set, depending on each of their values of u, which has to do with their values of y, z, x, and the current value alpha and beta that the program is evaluating. So this would be a maximum simulated likelihood estimator. So this finishes up this session of the maximum likelihood lecture, and the next session will cover the properties of the maximum likelihood estimator itself.